Now that we have learned the node voltage method is a kind of a shortcut for solving circuits, so we don't have to find our equivalent, and it saves us quite a bit of time, I want to introduce to you the mesh currents method. So let me show you an example circuit that would be a good candidate for using this method. Well, suppose we have a voltage source in parallel with a resistor, and let's put another voltage source here. Some more resistors and another voltage source here. I'm just going to label these generally, so I won't put in any numbers to begin with, so I'll do a specific example for you in the next video. So this will be voltage source 1, voltage source 2, voltage source 3. We'll call this R1, and this can be R2, and this can be R3. So it'll be helpful to have a circuit so we can write out all the steps for the mesh current method. So basically the process is, for step number 1, is we want to draw in and label all of the inner loops. Label all inner loops. So you may remember when we talked about Kirchhoff's voltage law that if we sum the current around any loop in the circuit, we'll get 0, right? So we're only interested in these inner loops here and here. We are not interested in like the composite of both loops or these wider outer loops, because they end up being redundant. So we're only going to label these inner loops. So I'll go ahead and call this one current 1, I1. This will be I2, and this will be I3. And I'll show you how these currents mesh. So the second thing that we're going to do, that's step number 1, is we want to label all of the loops. The second thing that we want to do, step 2, is for every loop we want to write the Kvl equation. So we're going to do the sum of voltages around each loop and set it equal to 0. So I'm going to say we're going to write the sum of voltages equals 0 equation for each loop. Okay, so some key things here is that with respect, we want to write our equation with respect to the current loop that we are walking around. So for example, if I'm currently making my equation for I1, I'm going to consider that the direction of this I1 loop is ground truth, like that's my positive direction. So you'll notice that when this current I1 gets to this R1 resistor, it looks like it's going this way through the resistor. But there's a current down here, this I2 current, that's also going through R1, but it's going in this direction. So the I1 current goes to the left, and the I2 current goes to the right. So these currents are going to mesh in our equation, and I'll show you how that works. So that's the key thing, is that your equations are going to be with respect to the current loop. And then the next thing is that if more than one current goes through a resistor, then they mesh. If more than one current goes through a resistor, then they mesh. Now the rule for meshing is if the currents are in opposite direction, we subtract. And if we are currently doing like the I2 loop, we're going to take I2 minus I1, right? So I2 is going to be considered like our positive current because we're currently doing the equation for the I2 loop. If then after that we're doing the equation for the I3 loop, then the I3 direction will be considered to be the positive direction. Okay, so if they're in opposite directions, we subtract the currents. If same direction, we add. All right, so I'll show you how that works. Once we've written all these equations, we're going to just solve the system. And you can solve the system of equations. In this particular example, we'll have 3 equations and 3 unknowns. You can solve the system using substitution, elimination, or matrix algebra, whatever your choice. So let me just go through really fast and show you how we would write these mesh current equations. So first of all, at loop I1, here are our mesh current equations. I'm going to start, say, like in this bottom corner, and I'm going to go around this loop and write the sum of voltages until I get to where I started, and then I'll set that equal to 0. So just basically the KVL equation. So we're going to use the passive sign convention, and so our convention is going to be that if our current is entering a circuit element through the positive or the negative terminal, then this is going to be a negative voltage. So for loop I1, this is going to be negative VS2 plus, now the next thing I'm going to encounter in my walk around my I1 loop is this R1 resistor. So this will be plus R1 times the current that goes through here is I1 in the direction of the I1 loop, and I'm going to subtract from that the I2 current because it's going in the opposite direction. So this will be minus I2. And this is how that I1 and I2 mesh. So by Ohm's law, this R times I gives me a voltage here. And once I have encountered this resistor, I pass through here, and now I end up where I started. So it means I can complete this equation with an equals 0. And this is my mesh current equation for loop I1. So how about loop I2? At I2, suppose I start in this corner. I'm going to walk around this I2 loop. The first thing I encounter in my walk around this loop is this VS1 source. So since I'm coming in through the negative terminal, I'm going to say this is a negative VS1. The next thing I'm going to encounter is this R1 resistor, but now, since I'm currently doing the I2 loop, I'm going to consider I2 to be the positive current, and I'm going to subtract from this I1. Whereas in my previous equation I did I1 minus I2 because I was currently doing this loop. Now I'm doing this loop, so this is going to be my positive current. So I have plus R1 times I2 minus I1 because they're in opposite directions. Now I continue in my walk around I2 loop. Next thing I'm going to encounter is this R3 resistor. So with the R3 resistor, on the left hand side I've got I2 current that's going through R3 in this direction. On the right hand side I've got the I3 current that's going in the opposite direction. So the way these mesh is they're going to subtract, and I'm going to subtract I2 minus I3. Okay, so once I've gone through here, I'm going to continue my walk around the I2 loop. The next thing I encounter is this R2 resistor, but the only thing touching the R2 resistor is just I2, so I don't have any mesh there. I just multiply it by I2, and now I'm back to where I started, so I complete the equation with an equals 0. Finally, at the I3 loop, if I start here, now I'm going to walk around the I3 loop. The first thing I'm going to encounter is this R3 resistor. So this will be R3 times, this will be I3 minus I2 since they're in opposite directions. I'm going to continue around my loop. Now I'm going to enter in to this voltage source through the positive terminal. So this is going to be a plus VS3. And I'm going to continue in my loop until I get to where I started, so I can complete this equation with an equals 0. Now this is the equations written using the passive sign convention for handling these voltage sources. If you like, you can use the opposite convention where if you are going through the voltage source this way, you can think of the voltage source as providing a positive voltage, and every time you hit a resistor, that's subtracting that voltage because it's a voltage drop, and the power is dissipated at each resistor. That's okay too. You just have to pick one convention and stick with it for the entire problem. So in the next video, I'll show you a specific example for applying this mesh current method to an equation with 2 loops.